mechanics with propagation of mode 3 cracks in bimaterial problems like the ones Nikolai presented yesterday when he torn apart a piece of paper. But we will be mostly focused on the behavior of the material close to the crack tip, where this region is usually called the process zone, that is usually introduced in mathematical models to describe the behavior of some nonlinear mechanisms during the fracture. So in the first part I will introduce a continuous model, which is basically here, and after that I will show a discrete model where we will have a set of point masses connected with elastic bonds, and I'll show the details later. Both of these problems will be reduced to Wiener-Hopf equations of the following form that takes place on the imaginary line of K, where A minus and A plus are the unknown functions to be found, and minus and plus superscripts denote the functions that are analytic in the lower and upper half planes respectively. And so the main problem is to factorize matrix M, which is of the following form. So our goals are to analyze the bridge crack for both cases, the continuous and discrete in mode 3, which means that the body will be in the antiplane deformation state. The second question will be how to factorize matrices of this form, not in general of course, but for these two particular cases. And after that we also want to understand how this parameter phi will affect the solution. So now we start with the continuous model. Consider we have two different elastic materials with shear moduli mu1 and mu2. These two materials are glued together, and in this interface we have a semi-infinite crack. In front of this crack we have the finite region that we call process zone, and after that there is a perfect interface. So the equilibrium state of the materials is described by the Laplace equation. Boundary conditions on the perfect interface assume that there is a continuity of the displacements and the tractions. In the process zone we assume the continuity of the tractions, while for the displacements we say that the jump of the displacements, or the difference, is related to the tractions inside this process zone through a constant parameter k. On the crack faces we assume that we have the out-of-plane external loading that is applied on the crack surfaces somewhere far from the crack tip. These conditions, also called the weak imperfect interface conditions, introduced in this paper by Gennady Mishuris and Natalia and Alexander Movchan, were used to describe soft thin adhesive joints. Here I will show some other existing models that are used. For example, the cohesive zone models introduced by Barenblatt, where it is assumed that the size of this process zone is comparatively small to the size of the crack, and the resisting force inside here are given in such a way so it will prevent this stress singularity. Here I will shortly remind what the stress singularity is. So if we have this crack, here is the axis, and as we get closer to the crack from this side, the distribution of stresses go like this, and they tend to infinity here, and the behavior is somewhat like this: k over square root x. So Barenblatt's model actually eliminates this singularity and makes the stresses to be finite in this region. Well, this similar model by Leonov, Panasiuk, Dugdale assumes the uniform distribution of these resisting forces gives the same result. In our model, which is more appropriate to call bridge crack model, we assume only the relation between the jump of the displacements and the tractions, and which doesn't give us beforehand the distribution of these resisting forces, so we don't know them, and it does not remove the stress singularity. So we will be using the fracture condition at the crack tip introduced by Irwin. So we will be looking for this stress intensity factor, and we will say that it has to remain below the critical value. Also, we will use the second fracture condition at the left edge of the process zone in terms of the displacement. So the jump of the displacement has also to be less than its critical value. Well, these Kc and Uc are given parameters and are parameters of the material. So here are the questions that we want to answer. First, how is this length of the process zone related to these fracture conditions, and how does it affect them? What is the shape of this red plot? After applying the Fourier transform to the original problem, we arrive at equation of this form, where W minus R is relates to the half-range Fourier transform of functions related to the displacements, while the V plus relates to the tractions. And the matrix looks like this, where note that parameter D is a material parameter. I will use it later. So K is the spring constant introduced before when we spoke about the model, and mu1 and mu2 are the shear moduli of the materials. So the main problem here is related with the presence of these exponential factors. And for this equation, we have two methods that we consider, one by Anastasia and the other one by Gennady Mishuris and Sergei Rogozin. But in this case, it seems more appropriate to use the first method. And at this point, I want to say thank you to Anastasia and to Matthew, as they already presented all the details about this method. So I will skip the details, and I will just show how the method works. So at the top figure, we have a parameter delta Fn, which is the discrepancy of the equation. So if we have the left-hand side of the equation, of the Wiener-Hopf equation, evaluated at some iteration n using this method, we compare that to the right-hand side of this equation, which is some given function, and the relative error of these two sides is shown here, and we see that it decreases with the iterations. As we can see that the method works better for rather large L. On the bottom figures, we show the convergence of the method. So we take the unknown functions R and Z and find the norm of the difference at each step, at each iteration. So here we basically show how accurate the method works, and here we show the convergence of the method. For the rest two functions that we had, these pictures will be the same. So now that after we found all the functions, we are able to go back to the original problem by using the inverse Fourier transform, and to answer, we're able now to answer one of the questions to find the distribution of these resisting forces inside the process zone. And as we can see that as we get closer to the zero, this distribution behaves as a square root and tends to zero, and not to be confused with that side. So if this is the process zone here, and it goes like this, the stress singularity is still there. And now we show the dependence of the stress intensity factor depending on the length of the process zone. Also, we show the convergence of the method in terms of these parameters. So we take the absolute difference of the stress intensity factor for each iteration, and we see that it decays. The same we do for the crack opening displacement. And now we can analyze how does L affect these parameters. So we can see that the crack is likely to propagate for rather small L's, while for the opening displacement, it's likely to reach the critical value for a rather longer process zone. But it's not really clear from these two pictures. So if we find the relation between the KL and the UL by excluding the length of the process zone, we can arrive at this picture on top. We see how the UL and the stress intensity factors are related, and it gives us this black thick line. Now imagine we have chosen critical parameters UC and KC, which is in the white region. We build the projections on this curve, and we find then that the equilibrium state of the crack exists only between these 2 points A and B. And from this it is possible to find the admissible values of the length of the process zone. Imagine the case if we take this point from the gray region, one of the fracture conditions will fail, or maybe both. Now, just to briefly conclude the first part, we have used an effective numerical method with good convergence, and we found the admissible values of the length of process zone for the static case. And now it is possible to analyze the case when we have a propagating crack. So if we say that the load that we apply here moves with speed v together with the crack, and it moves steadily, and the question then is the crack stable, and for what parameters? At this plot we show how the fracture parameters like stress intensity factor and crack opening change with the speed. So as the speed grows, the stress intensity factor decays, as well as the crack opening displacement, and this is how it affects the relation between these two fracture parameters. So imagine now we had for some speed v1 this relation, and if we had the case when the critical parameters were taken from this point, then for this speed the crack is not stable because one of the fracture conditions will fail. But if we increase the speed of the crack, and it will be fast enough that the curve will go somewhere down here and will be below this point, then we can conclude that increasing the speed makes things better for the stability of the crack. Yeah. Now I go to the discrete case. Now imagine if we have a set of masses connected with elastic bonds, where the vertical bonds have stiffness kappa and the horizontal strings have stiffness mu. Now also imagine that these bonds have different lengths, or if in the initial state we have compressed the even bonds and stretched the odd bonds and then release it, then at the initial state the odd bonds will tend to stretch while the even bonds will tend to stretch while the odd bonds will tend to compress. And if at some point while the elongation of one of the even bonds will exceed some critical value, it might break, and when it breaks it will release some energy which will be transferred to the next bond, which will also break. And in this steady state limit, such a process will form a bridged crack where only the even bonds are broken while the odd bonds remain intact. And then the question is, how do the micro level stresses appear due to this difference in lengths will affect the crack growth? This problem was considered and solved in the paper by Mark Eisenberg, Stepanenko, Gennady Mishuris, and Leonid Slepyan. It was also solved for a more general case for a square cell lattice. And note that in this case there was no external load applied to the system. Now if we take the same system and apply the external load, then we will have such a configuration. So here are the bonds, and here are the area that was broken. when we apply the external load, we tear apart this chain, and this will lead to the case when this bridge crack, unlike the previous case, will be of finite length. Then we introduce the total displacements of the upper ends of these bonds, where U0 is the initial displacement related to the pre-stress state of the chain. We introduce the critical elongations U, E, and UO. So when the critical or the even bonds elongate and the elongation exceeds the value UE, they will break. So the same for the odd bonds. Now if we introduce this parameter, which was introduced by Leonid Slepian, we will, oh, by the way, these functions UM are the additional displacements due to the dynamics of the fracture. So now we rewrite these functions in terms of new functions U and V by introducing parameter phi, which is a time lag, which says that at some point the even bond will break, and after some time the odd bond will also break. And this parameter phi shows us two things. First, it shows the length of the bridge track and the time when the odd bond will break. And so the fracture conditions in terms of these new functions will be rewritten like this. And this was all done so we can say that the odd bonds will break for the eta equal to 0, and the even will break at eta is 0, and the odd bonds will break at eta equal to phi. Also, here we say about the external load that is given by the conditions at the infinity. So the A infinity shows us how strong we pull. So the bigger the A infinity, well, the bigger the angle. So it means that we pull stronger. And now, so we have now the fracture parameters UE and UO, and the loading parameters U0 and A infinity, which we will use to find this parameter phi. Sorry for this long formula, but this is only used just to move forward to the Wiener-Hopf equations. So we will use the Green's functions, which appears when, imagine when we have the intact structure, and if we apply a single a unit load at the even bond 0 here, then the displacement due to this unit load at this point will be equal to that Green's function. And if we want to find the dynamic displacements for the general case and to collect all the forces in the system, it will be done by the sum of the convolutions with this Green function and these forces. Well, asterisks mean the convolution on time. And so we do that for the dynamic displacements for the even bonds and for the odd bonds as well. Yeah, and the phi is also introduced here. After application of the Fourier transform on eta and the discrete Fourier transform on the number of the bond, we arrive at the matrix Wiener-Hopf equation as shown here, which holds on the real line of K. The matrix looks like this, and there are several problems with this matrix. So the elements of the matrix have poles and zeros on the real line, and we again have these exponential factors which do not allow us to simply use the Liouville theorem. And the other one problem is that we don't know the parameter phi. So we cannot simply just use some iterative method to proceed. We have to do something first with this parameter. But still, if we somehow find it, we now remind these two methods I mentioned before, but in this case it is more appropriate probably to use the first one. Yeah, this function f is just the forcing term. Now, as Nikolai did yesterday, he had a matrix Wiener-Hopf equation. He introduced the sum and difference of the unknown functions which helped him a lot, but it doesn't really work in this case, probably due to the presence of this parameter phi. So what we also do, we transfer all the terms containing phi explicitly to the right-hand side. And at the first glance, it doesn't look like it's something very good, because we just have the unknown functions s plus and d plus on the right-hand side, and nothing really changed. But we did that only to see that if we put phi equal to 0, then this equation will be much more easier to solve, and this will be our starting point for the approximate solution. So we start with phi equal to 0 and analyze the system. In this case, these two big functions as and ad will be 0. Well, then we solve this equation in a way that Michael Neves introduced on his lectures last week, taking into account all the zeros and poles of functions ls and ld. Then we substitute the solution of this equation into the function as and d, and then somehow we use the asymptotics and the fracture conditions to find the value of phi, and we call that phi 1. Then everything that we found here we put back into the original Wiener-Hopf equation, and we have this, and then we just repeat the process. But so far we were able to resolve this problem for the case when phi equals to 0, and I will show some results for this case. As Mike Neves shown, these are the dispersion relations that come from the kernel functions of the problem that will show us how many poles and zeros we will have, and these in turn show us how many waves are excited while the fracture goes. And as we can see, that the lower the speed, the more of these zeros and poles we have. And here I will show just a few examples for the case phi equals 0. The red plot shows the height of the upper end of an even bond and its distribution over time, and we can see here that it does not intersect the dashed line in the negative time, which means that this case is admissible, that the even bond was broken at the time it was supposed to be broken, and the same for the odd bond as well. And we can see here that even for the case phi 0, there is a time lag. So at some time 0 the even bond was broken, and then after some time the odd bond broke as well. And the other one case for a lower speed, we see that this is a forbidden regime, because the height of the even bond was higher than it was supposed to be, so the elongation exceeded the critical value before it was supposed to do it, and so this case is a forbidden regime. And there might be also cases when it will be forbidden for the odd bonds. It could be for both, and all these things might bring to some different phenomena. For example, the fact that the exceeds the critical value before 0, it means that we have this fracture front, the crack front here, and as the wave excites towards the material here, some bond right here was also broken, and this should not happen when we seek for the steady-state solution. And such a regime is called the forerunning mode. And now to conclude, we have analyzed the bridge crack models for a few cases for the continuous, and partially for the discrete, only for the phi equal to 0. We have applied two different methods for matrix factorization, and as I've shown here, even though we can analyze the admissibility of the regime for the phi 0, there's still more to analyze in terms of how many different scenarios could be there. Thank you.
everyone is keen to go for lunch. If there are no questions, we can continue over the lunch break. Thanks very much.
Thank you.